Welcome back to Module 2 of our AI and Automation Masterclass. In today's explainer, we are doing something really cool. We're going to peel back the layers and look at how tools like ChatGPT and Claude actually function. I am so pumped to guide you through this because honestly, once you understand the fundamental architecture behind these models, it completely changes how you interact with them. We're going to pop the hood and demystify the magic. So, first things first, how do these bots actually find their answers? Let's clear up a massive misconception right off the bat. A lot of people think AI chatbots are just, sentient search engines looking up facts in some giant saved database. It's incredibly common to assume that when you ask ChatGPT a question, it scurries off to a vast digital library, pulls a pre-written file off a shelf, and hands you the answer. But that is fundamentally incorrect. There is literally no database of saved answers sitting inside the model.
The reality? It's honestly way more fascinating. They are actually statistical prediction engines built on a specific deep learning architecture called the transformer. Think of an LLM as a highly sophisticated autocomplete on your smartphone, just scaled up to a completely unimaginable degree. It doesn't know facts the way you or I do. It just knows the mathematical probability of which word should logically follow the previous one, based on the billions of texts it trained on.
So here's our roadmap for today. We'll quickly bust the search engine myth, dive into the transformer revolution, break down tokens and vector spaces, explore the self-attention mechanism, and finally wrap up with training and alignment. Let's kick things off with part 1, the search engine myth. If there's no database to search, what on earth is actually happening when it responds to you? Well, instead of searching files, an LLM generates its response entirely from scratch. It evaluates billions of probabilities to pick the most logical next piece of text. Every single time it spits out a word, it computes the statistical likelihood of all possible next words, picks one, adds it to your prompt, and then get this, runs that entire massive calculation all over again for the next word. It is continuously predicting the future, one tiny fragment of text at a time.
Moving right along to part 2, the transformer revolution.
To really grasp how this prediction happens so impossibly fast, we have to travel back to 2017 to a massive breakthrough by Google researchers. They published this now legendary research paper with a totally brilliant title inspired by the Beatles, "Attention is All You Need." Before 2017, older models like RNNs processed text sequentially. They read word by word, left to right. This was incredibly slow, and it suffered from something called vanishing memory. Basically, if it read a super long paragraph, by the time it got to the end, it literally forgot what the beginning was about. Transformers completely changed the game. Instead of reading sequentially, they look at the entire sequence all at once. They process everything in parallel.
What's laid out right here is the actual architectural blueprint from that seminal 2017 paper. Notice how it totally bypasses those old sequential bottlenecks. Because of this design, the AI can train on internet-scale data using parallel processing across massive arrays of GPUs. The training speed and scalability absolutely skyrocketed overnight. This single architectural shift is what allowed models to explode from millions of parameters to hundreds of billions, unlocking the crazy AI capabilities we see today.
Okay, part 3, tokens and vector spaces.
Let's zoom way in, down to the microscopic data level. It turns out AI doesn't actually read English words or letters. Instead, it uses tokenizers to chop text down into smaller, sub-word pieces. It turns a phrase like deep learning engineer into a series of optimal chunks. Think of these tokens as the fundamental atomic units of language for an AI. Sometimes a token is a whole word, sometimes it's just a syllable, or even a single space. The tokenizer just iteratively merges the most frequent characters it sees until it builds this highly efficient, custom vocabulary.
Now here's where it gets wild. These tokens are then converted into massive strings of numbers called vectors. And these vectors place words with similar meanings, like Python and code, super close to each other in a multi-dimensional math space. Imagine a vast invisible map with thousands of dimensions. The word king is placed right next to queen, but it's parked miles away from the word apple. This vector space is how the AI begins to understand semantic relationships. It's literally translating the human concept of meaning into physical mathematical distance. Which brings us to part 4, the self-attention mechanism. With our text broken down into pure math, we finally reach the true brain of the operation.
This mechanism calculates the mathematical relationship between every single word in a prompt to establish context. Unlike those older models that only looked at the word immediately next door, self-attention allows every single token to look at every other token in the sentence simultaneously. It figures out which words are paying attention to which other words, assigning different mathematical weights depending on their importance to the overall context.
Let's use a quick example. Think about the phrase, "the bank of the river." The attention mechanism helps the AI know that bank here means dirt and land, not a financial institution, entirely by looking at the surrounding context word, river. By scanning the whole sequence, the model dynamically adjusts the mathematical meaning of the word bank. Its vector actually shifts closer to concepts like water and nature and further away from money and vaults.
How does that actually do that? Well, each token emits a query, representing what it's looking for, and a key representing what it contains. Think of it like a crowded networking event. The word river walks in holding up a sign saying, "Hey, I am a noun related to water." That's its key. Meanwhile, the word bank is wandering around asking, "I have multiple meanings. Is there any water-related context around here?" That's its query. When the query and the key match, boom, they shake hands, create a high mathematical affinity, and the model instantly locks in the right context.
Finally, part 5, training and alignment. Let's zoom back out to the big picture. If we just stopped at predicting the next token, chatting with this AI would be a total nightmare. Training actually happens in 2 distinct phases. Phase 1 is pre-training, where the AI reads billions of web pages just guessing the hidden next word. It's absorbing raw data, learning grammar, memorizing facts, and picking up human logic. But if you asked it a question right now, it might just reply with another question, because it doesn't know it's supposed to be answering you. It's just completing text. That brings us to the crucial phase 2. This second phase is called RLHF, or Reinforcement Learning from Human Feedback. This is the magic polish. During this phase, humans actively red team the model, intentionally giving it tricky, weird, or harmful prompts. The model answers, and then humans grade those responses based on constitutional principles. It's basically sending the AI to etiquette school. It forces the raw statistical predictor to follow instructions, admit when it makes a mistake, and become the polite, helpful assistant you interact with today. So, we've covered a lot of ground today, from busting the search engine myth to vector spaces and AI etiquette, but I want to leave you with this final provocative thought. If an LLM is purely a statistical prediction engine that's just mapping tokens to guess the most logical next word, what happens when its most logical guess doesn't actually align with reality? This is the exact root cause of what we call hallucinations, and it highlights exactly why understanding this underlying architecture is so absolutely crucial. It is not a perfect, all-knowing oracle. It's a brilliant, highly educated guesser. Keep that in your back pocket next time you write a prompt. Catch you in the next explainer.